In today's lesson, we're going to look at multiplying radicals. So in last lesson, we talked about adding and subtracting radicals, and we learned that we were only allowed to add and subtract radicals that were like radicals, because the number in front of the radical told you how many of them you had, and to be able to add and subtract them, they had to be the same. So we have 5 of them, right? And so that was the rule with adding and subtracting radicals. So what's the rule with multiplying and dividing? Are we allowed to multiply two radicals that are not the same? So when we type in root 3 times root 5 on our calculator, do we get root 15? And we do. And same thing with 3 root 2 times 5 root 7. When we multiply those on our calculator, do we get 15 times root 14? We do. So multiplying radicals, we don't have to worry about having like radicals. We can just multiply the radicands together, and we can multiply the numbers in front of the radical together. Okay, so we just take a times c to get ac. We take the b times the d to get the answer under there. And it's as simple as that. The only thing that makes it a little more difficult is we have some simplifying to do at the end, because our final answer should always be simplified. So for example, if I go 6 times 2 times 10, I get root 120. But then we have to simplify. Oh, I can see that 120 is divisible by 4, right? And that's going to give us 2 root 30. Sometimes I can say, well, did I find the biggest one? I'm not sure. Could I have picked a bigger root? Well, take a look at 30 now. Does 4 go into it? No. Does 9 go into it? Nope. 16? Nope. 25? Nope. Okay, I did find the largest perfect square that divides into the radicand. And that's your final answer. Okay? And so if they're mixed radicals, you just multiply those parts together, the 5 by 2, and then you multiply the 3 by 12. And if you get under the radical a perfect square, well, then take the square root of it. Simplifying a perfect square, you've always known how to do. You don't break it into 2 parts. You just take the square root of it. 10 times 6, which is 60. All right. So if you ever get a perfect square under the radical, the next statement should have no square roots anymore, right? Because it is a rational number. And same thing with cubed roots, you do exactly the same. The 7 times the 1 becomes 7. Cubed root of 4 times cubed root of 6 becomes cubed root of 24. And then we simplify if possible. 7 times the cubed root of 8 by 3, because 8's a perfect cube. And the cubed root of 8 is 2. So we get 2 cubed root of 3, and then we can multiply the 7 by 2 and get 14 times the cubed root of 3. The only pain with cubed roots is you have to keep writing that index, right? So you don't forget it. So many times people forget it, right? Make sure you keep writing that index there, because it's important. It's part of the operation. So it's good to start to get good at multiplying and noticing shortcuts. For example, I would not go root 10 times root 10 is root 100. Oh, the square root of 100 is 10. We can make this a lot faster when you recognize that root 10 times root 10, well, you're just multiplying the same thing twice, so the square root is one of those. So whenever you have the same number under the radical, root 10 times root 10, the answer is just 10. Just like root 3a times root 3a, instead of writing 9a squared and then taking the square root of both of those, I would say root 3a times root 3a is just 3 times a. Right? And it just helps you out a bit. So I can get variables involved over here. So the negative 3 times the 7 is negative 21. And then I could write this out again, so you get faster. You may notice that x times x is x squared, which becomes x, but we can take it a little slower. We can get 6x squared, and then try to simplify the radical here. Well, 6 can't be simplified, but x squared can, because any even power is a perfect square, right? X squared, the square root is x. So it becomes x on the outside of the root, but the 6 stays on the inside. Okay, let's try a few more. Again, fractions. So 4x squared times 1 just becomes 4x squared. And then we have a fraction on the inside, so basically we have 21x over 1 being multiplied by x over 7, which becomes, and I'll rewrite the 4x squared, 21 divided by 7 is 3, and x times x is x squared. And again, we're going to simplify. The square root of x squared is x. There's already x squared out there, so it's going to become 4x cubed. And the 3 stays on the inside. Okay, let's try one more. Sometimes, if you take 18 times 20, and you get a large number, sometimes it's easier to simplify first. This is not that large, so I'm just going to multiply right away and get 360. But sometimes it's easier just to simplify first, then multiply. When you get really large numbers under there, this one's pretty easy to handle because I can see it's 36 by 10, right? And so the square root of 36 is 6, so 6 times 15 is 90, and I get root 10. All right, so multiplying is basically multiplying and then simplifying, right? Or simplify then multiply. It's important to remember that when you are multiplying, they have to be like indexes. So if it's a cubed root multiplied by a square root, then you couldn't do it. All right, so only if they are the same roots, both square roots or both cube roots. You should be able to combine your addition and subtraction and multiplication through your distributive law. So if I want to multiply 3 root 5 by this set of brackets, then I just distribute it to both. Okay, 3 times 4 is 12, 5 times 2x is 10x. And then minus 3 times 2 is 6, root 5 times root 5, this is where we want to save ourselves some time rather than writing root 25. I know it's just 5. And then we simplify where we can. This first term cannot be simplified, but this becomes 30, right? Because that's multiplication. When you have a binomial multiplied by a binomial, we need to use our distributive law twice, right? Or FOIL, however you want to understand it. So the first one needs to go to both. So 2 times 2 is 4. Root 3 times root 3 is 3. Then we do the next one. Positive times a positive. So I'm going to get 2 times 1 is 2. Root 3 times root 2 is root 6. Now I'm going to do the next one. A negative times a positive is a negative. 3 times 2 is 6. Root 2 times root 3 is root 6. And last, a negative times a positive is a negative. We get 3 times 1 is 3. Root 2 times root 2 is 2. So the roots disappeared in the first product, and the roots disappeared in the last product, right? But the middle, the outer, and the inner product, they're still there. So now I'm going to simplify. So I'm going to get 12 minus, let's just write it all out. Plus 2 root 6 minus 6 root 6, and then minus 6. Right. Now I'm going to collect like terms. 12 minus 6 is 6, and 2 root 6 minus 6 root 6 is negative 4 root 6. So I multiplied it all out, and when you're collecting like terms, you add like radicals, and you add the constants. If you're squaring a sum or a difference, you can't just square each term. You must write it out twice, and do exactly what we did in the last question. We need to use our distributive law twice or FOIL it out. So we're going to get root x times negative 3, which gives us negative 3 root x. Oops, I don't know why I started with the outer. Let's start with the first, what I normally do. So root x times root x is x. Then root x times negative 3 is negative 3 root x. And then we go to the negative 3 part and we distribute it. So negative 3 root x. And then negative 3 times negative 3 is positive 9. Again, collect like terms where possible. X has no like terms, 9 has no like terms. Those are the only two terms we can collect. So we're going to get x minus 6 root x plus 9. And that's as simplified as we can get. We can't simplify the root x because x is not a perfect square. All right, maybe pause the video, try this one on your own, and then check to see how you're doing. So let's use our distributive law. Let's do some of this in our head to save ourselves some time. So 2 times 2 is 4. Root x times root x is just x, right? And then outer one becomes positive 2 root, and x times y just becomes xy. And then now we're going to distribute the negative y, root y. So I get negative 2 root, and I could write yx, but I'm just going to switch it to xy because order doesn't matter when you multiply, and then it just makes it nice if they're always written the same. Easy to find our like radicals. And then a negative times a positive is negative, and root y times root y is just y. Okay, collecting like terms where necessary. The only like terms again I see are my radicals. So I get 4x, and then 2 root xy minus 2 root xy becomes 0 root xy, so they actually add to 0, so they're gone, and then minus y. So that all just gets me to 4x minus y. Okay. These two are actually called conjugates, right? A conjugate is when you have like root 3 plus 1, and the conjugate of this is the exact same thing but opposite sign, right? So if it was adding, I'd write it all but subtracting. If it was subtracting, the conjugate would be the adding of the same two terms. Whenever you multiply conjugates, you'll notice that the first times the first, right, and the last times the last are there, but the outer product, the negative 3x, and the inner product, the positive, root 3, they always add to 0. They cancel each other out always. So whenever you're multiplying two of the exact same binomials, but one is plus and one is minus, that will always happen. And we're going to work with that a little bit later in another chapter, but it's a good little point to bring up there when you're doing that. That always happens with conjugates. All right, let's do one last question. Let's determine the area and the perimeter of the inner square. So we have this inner square, and this whole length is 8. Since that whole length is 8, and I know these two lines are here, that means they both are 4, right? And that's 4 as well. Okay, so since I know these two sides of a right triangle, I can then find this side of the square, right? It doesn't look like a square. My drawing's not so great, but this is a square because I told you it's a square. Anyway, this is a right triangle here, so I can use my Pythagorean theorem. X squared equals 4 squared plus 4 squared. X squared equals 16 plus 16, which is 32. So x is the square root of 32, right? Or in simplified form, 16 by 2, x is 4 root 2. Okay, so I now know what x is. So now I just want to know the area of the inner square. Well, the area of a square is length times width, right? Is the area. Well, I know the length is 4 root 2, and I know the width is 4 root 2. So I can use that to find the area. The area is going to be 16, right? This is area. It's going to be 16 by root 2 times root 2 is 2, so the area is 32. That's the area of that square, okay, the inner square inside. And I know the perimeter, because I know the perimeter of a square is the length added up 4 times, or 4 times the length of the square, since they're all the same, right? So 4 root 2. So the perimeter is going to be 16 root 2 in exact form. So that's the perimeter, whatever units we're working in, and that's the area of the inner square.